Welcome to this session of this technological chair. It's my pleasure today to introduce Benito Allen, the speaker of today, who is a rare mixture, a rare blend between very interesting scientific achievements and entrepreneurial activities. So he did his undergraduate student studies in different universities. Let's say he explored the Spanish geography for a while, and then he did a PhD in Valencia, already in the field of quantum dots, or optical properties of quantum dots. Then he did a postdoc where he contributed to one of the first measurements of fluorescence in quantum dots, came back with Juan de la Cierva to the Institute of Nano and Microelectronics in Madrid. Then he became Ramón y Cajal and worked a little bit between ICFO, because it was a collaboration between the two, between ICFO and the same institute. And then he got a permanent position at the Institute of Nano and Microelectronics, where he's working. He has been, as I said, doing very important contributions to the physics and technology of quantum dots, especially with the application of developing single photon sources. And perhaps as a byproduct of the crisis we had during 2008 and 2014, and perhaps even now, actually he profited to turn a problem into an opportunity, and as a result, he got an idea on how to solve some of the problems that these systems have, how to solve the problems that some of these single photon sources are facing worldwide. And he got an idea, and this idea has crystallized in some of the things he will tell us today. And also, and I think this is very interesting, as I told you, it's a rare blend, but I think very important, this basic science led to the development of an idea that now is trying to develop in a company that is g2-ZERO, which apparently is a very important parameter for the people who are working on single photon source. So I'm going to stop. I'm glad that you accepted the invitation, and the floor is yours. Thank you very much.
Thank you very much, Fernando, for the kind introduction. Marta, for the invitation to be here today. As Fernando just said, I have two hats at the moment. One is my position as científico titular in the Institute of Micro and Nanotechnology. I think I need to share this. Not seeing. No.
¿Ahora?
No tiene simetría. Okay, there. Okay, good. In the Institute of Micro and Nanotechnology at Madrid, Tres Cantos, and then since 2020, we have started this adventure with the spin-off company g2-ZERO, which is a EBT of CSIC. It's a Empresa de Base Tecnológica, according to the program that the O3 of this institution has to transfer technology results. Okay. So the context of my talk and of whatever we are doing. Technologies. Okay, now it's working. Okay, So the context where I want to put my talk is the context of uprising quantum technologies and demands of quantum technologies for solving the challenges of the future, which ones of them are posed as problems and ones of them are posed as solutions for those problems, okay? So we are all very aware of how much the academic and industry is focusing on the development of a real quantum computer, okay? And there are many possible implementations. Some of them are being pursued here at the institute itself, okay? And the point is that, well, as a drawback of all this development, one of the uses of a quantum computer might not be as good for society as one would expect, since we know that public key could be broken, okay, by a quantum computer using algorithms such as the short factorization for prime numbers. While this might be a long-term threat, okay, we should be ready for whenever this happens. So, for instance, the NIST said that maybe already in 2013 there would be a quantum computer able to factorize an RSA public key of 2000 bit. Okay, we don't know whether this will happen, but if you want to know about what are the threats that this might bring, I recommend you this dissertation by Michel Mosca, where he said that whenever this time comes, we need to start getting prepared by now. We should not wait until the quantum computer is here. The good news is that the quantum world itself brings a solution, and the solution is using quantum states for encoding communication information. So the kind of telecommunication that we do now, encoding information in classical bits that travel as light across optical fibers or RF signals from mobiles to antennas and so on. If we bring all this to the quantum, then it's possible to build completely secure quantum communication systems, okay? So this is already a reality in the sense that the Chinese on 2016 launched a satellite, which of course they have started to plan way before. You don't send a satellite in a few months, right? And the satellite itself was able to establish a quantum link between 7,000 kilometers between Austria and Shanghai in China, okay? Relying on entangled photon pair generation and entanglement of these two photon pairs. Okay, the whole thing has driven a big interest, okay, for terrestrial and for terrestrial satellite communications, quantum communications. And today there are many space agencies, okay, which are seeking for establishing quantum links, either sending secure key rates uplink or downlink from satellites to ground to satellites. Okay, the reason for using the satellites is that in fighting with the losses that are inherent to any transmission system, a transmission of a low signal, we see these are low signals, needs to travel only 100 kilometers if it goes to space. Once it's there, it can be transferred between different satellites on a vacuum environment, okay? This is apparently more efficient than trying to travel 14,000 kilometers through optical fiber by submarine cable or whatever. The main actors are China, Canada, and the United States. For some reasons, and the European Union, for some reason, the United States are pursuing post-quantum cryptography approaches, which do not rely on quantum communication at all, but rely on more computational security as the public RSA protocol that we have right now. There are several ways of doing this. All of them depend or the differences between them depend on the kind of source that we are using to encode the quantum information, whether it is the Cori state, which basically is a wake laser source attenuated to the point where it emits a very small number of photons, but you never are sure that it is one or more than one, or entangled photon pairs, okay? And well, the terminology of trusted nodes refers to the fact that in order to transmit a quantum key from one point to the other, there is a limitation, which is the distance at which we can transmit them, because there are losses along the way. Single photons are lost, or the signal are lost, so we cannot go indefinitely far. So typically, every second node, we have to replicate the key or send again a new key. So in order to establish a quantum link over big distances, all these satellites need to be trusted, needs to be with the ally, not with the enemy. There are other protocols which are based on device-independent QKD, where the nodes do not need to be trusted because there is no information stored at the node itself. So we send the communication from A to B without relying on whether the node in between it's from an ally or from a potential enemy. But so far, all these are based on trusted nodes, except in Misios, which was a demonstration of a device-independent protocol, potentially device-independent. So the whole QKD started in 1984 with the BB84 protocol, and in the original form it was based on single photons. Okay, so single photons means that we have encoding information in one quantum bit, which fully obeys the uncertainty principle of quantum mechanics and no cloning quantum theorem of quantum mechanics. If these two things are fulfilled, then it's possible to exchange information, being sure that nobody can hack the information, okay? So basically, Alice needs to send random bits in a random basis for polarization of these two photons, so that we don't know whether we are detecting in the HB polarization basis the single photon or in the diagonal anti-diagonal. This is important, and this is kind of a result of the superposition principle. Okay. Then Bob detects also a random basis. Bob doesn't know which basis Alice was using for the encoding. And once all the communication has finished, they publicly exchange the basis. Okay. By doing so, they know whether they were measuring on the same, they were emitting and measuring on the same basis or whether not. If they were measuring, emitting and measuring on the same basis, it's possible to reconcile a key, a one bit of quantum information exchange, and if not, this bit is discarded. By doing this, it is possible to avoid Eve being spying the single photon, because no matter whether she takes the photon, it will be one photon that she needs to replicate. And the no-cloning quantum theorem tells us that she cannot replicate that photon because she doesn't know the basis, okay? So with this simple protocol, the quest started, or whether we can build such a system, okay? Such a system will have security based by laws of nature. The security of the quantum key is verifiable because it's based on devices which we know how they work and on which basis they are emitting the information or transmitting the information, and is secure against present and future attacks. Not like the public exchange key protocol, the RSA protocol that we have now, that relies on our we being unable of factoring prime numbers with our current resources that we don't know in the future. Okay. And it might, in principle, enable all kinds of cryptographic primitives for different applications, not only for message encryption, but for all these applications. So regarding how far we are to have a practical system, the optical terminals are already in a technology readiness level of 8 to 9. Okay, this is very important for anyone asking for a applied proposal, funding for an applied proposal, or for companies in the developing state. Okay, so TRL9 means it's already in the market and mature. Okay, so TRL9 we have only for optical terminals. For detectors, we have quite a number of detecting technologies which are quite good for this purpose. Okay, so we could say that is in 6.7, but for the sources, we are a little bit below. And there are several ways and several physical platforms where to develop sources which are good for QKD. Okay, we have just figured out one of them. Okay. Beyond QKD, quantum communication is much more. Okay, so there is also the proposal of building quantum communications as a way of connecting mainframe, the quantum computers to the mainframe, so people can access to the quantum computers in an anonymous way, get the results in an anonymous way, or even teleportation protocols, and all. So I just put this picture because the guy who sent the satellite to the space in 2017 is Yang Pang, and right now is the person leading quantum communications in the world. Okay, and already in 2021 he started to know about quantum dot single photon sources, and he wrote a review. Okay, a review on Nature Photonics, I think, saying that probably we should follow this path, okay, to establish the quantum internet. Maybe for QKD and short distance communications, there might be other solutions, but for long-term quantum communication deployment, quantum dots are probably the best choice. And just as an example, here is the reference, okay? So to explain briefly what a quantum dot single photon source is, a quantum dot is made out of two semiconductors with different energy band gap, okay? And basically the energy levels inside behave as an atomic system, okay? A single atom. So the levels are quantized, and due to the Pauli exclusion principle, whenever a carrier recombines on these atomic levels, it emits a single photon. That's it. The question is how you put the carriers inside, how you collect the single photons out, and all that. The working principle of the quantum dot is that of an atomic atom, which can be embedded in a solid state environment. And then they are embedded on photonic cavities because, okay, we have the photons inside the material, but we want to connect the photons to the outer world for the application, right? And we will see how. Okay, so just as a very recent application of these ideas of Yang Pang group, okay, so we have this example of a quantum interference experiment. So this is aiming to device-independent QKD. So for that, it's important that the two sources emit indistinguishable single photons. We will see what is this, okay? Across 300 kilometers of fiber, okay, and at telecom wavelengths. And this is kind of a hallmark of one of these communication nodes of the quantum internet, okay? Indeed, in this case, there are two different quantum dots, okay, which emit photons which are slightly different in wavelength, but once they are down converted to telecom wavelengths, the emitting wavelength is made the same by a down conversion process over here. And then over here, what we have is the Bell measurement that allows to transmit the information from one side to the other. Okay? So this is kind of building component of the quantum internet that other people is developing, okay, based in quantum dots. There is yet another example from Yang Pang of the applications of single quantum dot, single photon sources, okay? And in this case, it's in the context of bosonic boson sampling, okay? Boson sampling is not a universal photonic quantum computation operation. It's just a kind of problem where a photonic quantum computer can do better than any classical computer. So it's good for demonstrating quantum supremacy stuff. And indeed here, again, we have a quantum dot embedded in a photonic environment, which is spatially demultiplexed, okay, and goes into a multi-mode interferometer where the photons can interfere with each other, okay, and then out of these interference paths, which are difficult to calculate classically, they are projected in different reading channels, and we get the statistics of this problem. And this is something that demonstrates quantum supremacy, okay? So this is, there is beyond QKD, there is a large interest in having efficient single photon sources, which can be used for photonic quantum computation as well, okay? The same way that is being used with superconducting quantum bits or spin qubits or whatever. Photons are also good for photonic quantum computation. And in this case, for instance, well, it was a 16 megahertz single photon source. So the rate for was 16 megahertz. So this is all we need to know about single photons to understand whether a source is good or bad. Okay. So brightness, purity, and distinguishability. Brightness is clear, no? How many single photons we can put per second in the channel, in the wavelength channel, spatial channel of my application. The higher, the better. If we can have a 1 gigahertz of single photons, it would be better than 1 megahertz. The other is the purity. Okay, so I can put many photos, but I need to know that in any instant of time, in any given slot of time, there is only one photon in the channel, and that photon has been put there by me. Okay, so this is deterministic single photon generation. It distinguishes some sources from other sources that can have a high rate, but they cannot put the photons in a given slot. Okay, single photon quantum dots, single photon sources based on quantum dots are deterministic and of high purity, which means that we don't have more than one photon at a time in any given time slot. And the last one is indistinguishability. Okay, I can have many photons, always one photon at a time, but they don't need to be the same. This is important for any protocol based on quantum interference, but not all protocols needs of quantum interference. So these three figures of merit distinguish the kind of single photon sources that one can produce. So there are those that produce a pure focused state of light, like a single photon source or entangled photon source. So there is either one photon, no photon, or two photons, and those that create a superposition of focused states. So you can say that at any given moment, there is a good probability of having just one photon, but you are never sure whether you might have more than one. And here is the category for weak pulse lasers and for parametric time conversion single photon sources. Okay, so there are ways in these two cases, there are ways to make them better and make them as good as it would be a pure single photon source, but typically are tricks. Okay, the ideal would be to have a pure focus state in a solid state environment or in a high brightness, high purity single photon source. So regarding technology, of course, I already said that quantum dots are like atoms, so we can trap atoms. We know that. In the past, it was done on vacuum chamber. This was the work of the group I collaborated with at ICFO at my time there. But now this is typically done in a chip. So it's possible to put single atoms and confine them by electrical traps already in a chip. And then doing the same route for an SPDC sort, which started like an optical table sometime in the 90s with many beautiful demonstrations and important contributions, okay? And now they can be done also on chip, okay? But when it comes to real miniaturization, to real having as much good use of material as possible and compact designs and all, it seems that solid state is the best natural choice for developing a single photon source. And here again, we have quantum dots made out of 3-5 semiconductors, which, as I said, okay, are similar to artificial atoms. Their photonic environment can be engineered. And most importantly, in this case, the electronic environment can be engineered, so they can be electrically driven and electrically tuned, okay, which is not so straightforward to do. For instance, when the quantum dots, when the source is embedded in the electric environment, where it is difficult to make an electric contact to inject carriers to, okay? And then there are emerging technologies that, like 2D materials, which want to catch up with the results of done on quantum dots, but so far might have problems. They work at room temperature, but then so far they might have problems of resilience over time, okay? So are material less known and in principle more chemically unstable than semiconductors so far, so well known. So there is, here I put a table, okay, of what was the best performance in each category at the time we started with this investment of the company in 2019. So here there is a report where you can see what are the best single photon sources results available at the time, depending on the system, okay? And for quantum dots, excepting for, I think, entanglement fidelity, which is lagging a little bit behind SPDC, in all other categories is the best, okay? Especially I would like to point out to the brightness. So this was a 30 megahertz single photon rate count, okay? And the purity of the source, okay? So this is with resonance pumping of the resonance fluorescence, indeed, of the single quantum dot. So the dot is pumped optically on resonance with the two-level system, and it's 7 times to the minus 5. Okay. Yeah. And then, well, up to very recently, to 2022, there were not clear comparison of the future of single photon sources based on these two-dimensional materials or two-level systems with well-known protocols based on decoy state and will pulse lasers and so on. But there is this work, at least, that I can cite now, that is already published, okay, where they compare, okay, the secure key rate, okay, which depends on brightness, purity, and loss of the channel for a standard decoy, okay, which would be this line over here. More modern protocols like the twin field based also on weak laser pulses, okay, and state-of-the-art single photon source made of a quantum dot. And a state-of-the-art means they are not a state-of-the-art, but this region here depends on the collection efficiency. So as we get better extracting photons out of the semiconductor material, we will get better collection efficiency. And for instance, for efficiencies around 30% or 40%, they already can exceed the secure key rate, okay, based on brightness and purity expected for this single photon. So, and these are different pumping methods. So this is just for, telling you that there is an ongoing interest in developing single photon sources. This is to be applied in an important market, okay? So far, there are working technologies that catch up with the need so far, but the idea is that the pure single photon sources would be deployed in the future in applications where now we have with pulse lasers, okay? So what about when we want to put the single photon source not only in a discrete element, like it would be needed for a 2KD system, but we want also to make this for integrated quantum photonics, for instance, for a boson sampling application. So in that case, it is clear that we need different single photon sources aiming to different spatial modes, okay? And imagine that if we want to do this with every source emitting at the same wavelength, being indistinguishable in big numbers, the best would be if we can electrically drive the emission of this, so we don't need to optically pump each of these sources individually with different lasers and maybe different wavelengths, and also that they are tunable, okay, electrically tunable. In that sense, they all can be indistinguishable and being driven in the most compact form factor for the chip, okay? So it turns out that having a single photon source that simultaneously can be electrically driven, electrically tuned, and is compatible with an integrated photonic environment was not possible. And there is where I had that idea of 2017, okay? So this was the birth of the g2-ZERO. g2-ZERO birthday was to develop ultra-compact semiconductor quantum light search for the development of quantum communications and computing applications. g2-ZERO has proprietary designs which are based on materials and techniques which are extensively studied and used anywhere in the world of optoelectronics, so are reliable and scalable. Okay? The know-how that we exploit is based on our research, the research of my group, the Molecular Beam Epitaxy group, who I'm a member of, okay, at the Institute of Microelectronics and Nanotechnology in Madrid, where we have been developing 3-5 semiconductor solutions for more than, me personally, 23 years, senior members of the group even more. No? So we have everything that is necessary. MB epitaxial growth, these samples do not grow on trees, they need to be grown on a high vacuum reactor, clean room fabrication with state-of-the-art techniques, and then a quantum nano-optics characterization laboratory, which is my laboratory. Okay. Well, with this, we have developed different demonstrations. Okay, maybe this is worth to be highlighted. This is an array of single photon sources. Okay, already each one of these is a single photon source, which is located in a given position in a system, which turns out that is not a standard way of getting them, but well, we didn't pursue this idea. Well, it was quite new at the time we did. Well, we can play with any material. 3-5 semiconductors are flexible on combinations of band gaps to target different wavelengths. Well, we have choose a particular 3-5 system, which is gallium arsenide substrate and indium gallium arsenide-based materials. But whatever I'm showing here today, it could be done with tungsten monides, with phosphides, with nitrides, with the same idea. Okay. So as I said, well, what would be the requirements for a plug-and-play single photon source? Okay. So we want it to be electrically driven. So, well, this was already demonstrated by Toshiba in 2002. How do you make a single photon source, semiconductor single photon source, electrically driven? Very easily, you put a quantum dot inside of a junction diode, inject current in the junction diode, electrons come from one side, holes come from the other side, they recombine inside the quantum dot, and as a function of the current, we have emission, okay, spectral emission on an atomic line, which turns out that we call it X for exciton, one electron hole pair, okay? And all this line and this line both are good single photon emitters. The problem is that if I want to increase the brightness of the source, I can only increase the current. And if I increase the current, I will change the wavelength because I have no control over the wavelength, okay? So this can be done, okay? So it's first tick, okay? The second that is we want to do exactly the same, but in a nanophotonics environment. Why? We will see why. We need to get the photons out of the semiconductor. And here the problems start. If we want to inject electron and hole pairs inside of quantum dot, which is embedded in a quantum nanophotonic environment, we have the problem of the heat resistance. Any nanophotonic environment is based on a modulation of the dielectric function in space, which typically brings the electrics in the equation, air, sodium dioxide, or whatever, and this doesn't transport charge, okay? So whenever people has tried back in the time to put a single quantum dot inside a nanophotonic environment and inject current, the results were very pure, and nobody succeeded in doing that efficiently, okay? But it was possible to do a wavelength tunability. This time, to tune the wavelength of a quantum dot or an atom, we rely on a star shift, and a star shift is something that relies on voltage in capacitive coupling of the two-level system with the electric field, and here the heat resistance doesn't play any role. So here you can see an example back in the time as well, where inside a photonic crystal cavity, there was a quantum dot whose levels could be tuned by an electric field. Here we are varying the reverse electric field on the junction, and that way we could put into resonance the photonic mode and the two-level system emission. In this case, for the application of finding a strong coupling between them. So this was possible. So the question is, okay, we have two or three, but how to solve the problem of to have the three of them? And here is where the idea came, okay? And it came by three groups at the same time in 2017, okay? The first group were the inventors of the quantum light emitting diode, so the patent on paper of 2002. The other was the Technical University of Berlin, and the other was us in the context of an Explora project. Remember when there were no projects, national plans were scarce and all. So I submitted an Explora with this idea, and since the funds were not enough, instead of submitting a paper or trying to write a paper, I submitted a patent, okay? So the idea is how we do this, how we get electrically driven nanophotonics embeddable and wavelength tunable. Well, now it seems easy, but nobody relied on that. Nobody knew that before. We need to split into the function of the device. So we can have a master diode, which is electrically driven, where we can inject current, which emits classical light nearby to a slave diode, which contains a quantum dot, a single photon emitter of any kind, which absorbs that light, and where we can apply a reverse electric field. So this way, the whole device will be electrically driven, the single photon emitter will be tunable electrically, okay? And everything will be compatible with a nanophotonic environment, like here for a whispering gallery. Here, the slave is a quantum dot, which is sitting on this edge of the whispering gallery. So it's a nanophotonic environment. It's pumped by classical light by the master diode, which is absorbed here in the form of photocurrent and re-emitted as single photons. Just the same way that would happen if I pump the quantum dot directly with external laser. So it's like building my external laser monolithically in my device. Okay, simple. Well, we focus on instead of this lateral arrangement of master and slave diode, we focus on a vertical arrangement of the master and slave. Okay, And in principle, it allows both to have a quantum photonic circuit, single photon source, in the way that we can pump a quantum dot, which is embedded in a photonic crystal cavity. So there will be some sacrificial layers, some slab over here, but it doesn't matter because the coupling between both is optical, is galvanic, okay? And then this light will come in the waveguide, okay? Or it can be used for discrete elements coupled okay? The good thing of not relying on an external optical source is what is plugging or experiments so far down in this field, which is you need to align your laser with your single photon source, okay? Imagine the single photon source is 1 micron. Single photons are by definition very faint signals, so you need a very good optical microscope. In my case, it's a confocal microscope working at 4 Kelvin to extract the single photons out and to make it run for hours. Or if it's for application, weeks, months, and so far. So by bringing them together and monolithical, you get rid of the alignment problem. It's alignment free. The second thing is that we might think of this device being exploited, I don't know, in a ship, for instance, or in a satellite. Okay, what about vibrations? Okay, this will never move relatively to each other. So it's vibration resistant as well. And one is said, you don't need somebody taking care of a microscope on a single photon source. It's set and forget. It's pretty much as a transistor, a photodiode, or a laser. There is a knob, you switch it on, and there are photons coming out of the phone. So the point is how to make this a product out of it. So as I said, we submitted the patent and we immediately started to develop the technology, okay? So this is an example of the first generation of devices. So this is a PNP double junction. The first PN junction is for the classical diode. The second one is for the quantum diode. The quantum diode has quantum dots, and the classical diode is a multi-quantum well light emitting diode, big cell, resonant cavity light emitting diode. There is no restriction of what can we put here. We can put whatever good component, and even we can buy a commercial component and regrow our quantum LED on top. That's a big advantages. This technology is all new. We don't need to develop it, okay? And then over here, you can make use of anything that has been working so far in the field. Photonic crystal whispering galleries. From this position up, everything is like a regular sample, okay? So we fabricated it and we need to test it electrically. So here the trick is we have a PNP, which those of you that have done electronic courses, you know this is a BJT transistor structure, but it's one with a very bad base, okay? We don't want majority carriers to cross across the base. So this would be the emitter, collector, and base. We engineer the base in such a way that the coupling between both is optical. We don't want carriers to transferring across the device, okay? And when you do that properly, the transimpedance case of the transistors is equal to 1. And this is the output of a very bad transistor. This is what we want, okay? Beta equal 1. If it were a good transistor, it would be beta equal 40, beta equal 100, or whatever, okay? And then we have two control knobs to control the device. One is the master diode knob, where we control, this is the IV course of the master, so we control the current of the master, working over here on the forward bias, okay? And then we have another control for the slave diode, where we tune the wavelength, working with the reverse bias on the slave diode. And the coupling between them is the photocurrent. As I increase the master current, there is electroluminescence generated here, which crosses the devices, is absorbed here, and we can measure as current in the slave diode, okay? And the coupling with them is the linear and photocurrent. So this could be more or less expected, or well, we expected. I had biggest uncertainties on whether this would be ever possible, okay? So this is the lighting, is typically the light in, light out characteristic of a single quantum dot in the single photon regime. What we see here is the intensity of the different atomic lines, okay, so to say, of the quantum dot, okay? The first thing we notice is that the quantum dot looks pretty much, looks exactly as if one would have excited externally, the quantum dot with an optical pump. In terms of line width, in terms of splitting, in terms of behavior of all kinds, this is a quantum dot optically pumped for the quantum dot itself, okay? And then instead of having lighting, which is power of external laser, what we have here is the master current, is the current that is being injected in the master, okay? So this effectively increases the parameters of each of these lines, okay? So at saturation, where this line gets the most intense possible, we get 1 gigahertz of photons inside the semiconductor. We know that because we can measure the lifetime of this quantum dot for this line, and we know it's 1 nanosecond, okay? So it's producing 1 quantum dot with a lifetime of 1 nanosecond, okay? It's at saturation, so it means that at this point, I'm charging more than 1 electron hole pair per quantum dot, and then the line goes down. The intensity goes down because of saturation. But in my first lens, I only have half a kilohertz, okay? And this is related with the fact that we need a photonic environment to do the things better. Okay, this was done without heating, without any, without heating in the sense, I was expecting having problems, like ramping up the current and heating up the device, and the game is over, okay? No, this was done at very low current. This is actually milliamperes per centimeter, but the consumption was 7 microamperes on the master. So we saturated a quantum dot out of a device that was consuming 7 microamperes, okay? And this is the image, okay, of the device on the confocal, okay? So at 780 nanometers, we have the emission of the master, okay, which is illuminating all this area over here. The light partially goes out because the upper mesa is not big enough to absorb everything. And then at 930 nanometers, at this wavelength, we have the emission of the quantum dots being excited by this one, okay? So far, at the single photon 4 Kelvin level is working, but we need to measure g2-ZERO. And our company is called g2-ZERO because to demonstrate that you have a single photon source, what you do is a Hamburg-Brown and twist experiment, which gives you the value of the parameter g2-ZERO. So in our case, g2-ZERO is not 510 to the minus 5, as when you drive resonantly with resonance fluorescence at quantum depth, but for non-resonant pumping, this is a state of the art, okay? So we get 0.9% purity of the quantum dot at 7.5 microamps driving. So we have the electrically driven SPS, and what was for mining was to demonstrate that it's tunable, okay? So what we do here is a series of experiments where we change, as before, we set the master current, okay, to 10, 20, 30, 40, 50 microamps, which effectively corresponds to different brightness of the single photon source. And then I tune the slave diode voltage. And what I have is the standard star shift of the lines. So I'm tuning the wavelength electrically while I'm driving the single photon source electrically. And if I do the other way around, what I want is, okay, I fix the wavelength, I fix the wavelength of the slave, and I change only the brightness by increasing the current of the master. And I see that there is a small shift, but the shift is 10 times smaller than the wanted feature, which is the tune, okay? And all this could be scaled up, putting proper barriers and all. This was just the first prototype, okay? So with this, we have electrically driven, electrically tunable, and we repeated this in order to make our life easier, okay? This was 2019, 20, well, pandemic, just before the pandemic, okay? Where we had our new generation of devices, where we have already packed 18 devices in a single chip, okay? Everything ready to continue doing experiments. And in this case, the form factors were different. The size is still 30 microns, okay? Not 25 as before, 30 microns. Currents were a little bit bigger because the base and emitter were a little bit bigger, but the main features, tunability and stability were there, okay? So what is left? Is left the photonic integration, okay? Why? Because we have only half a megahertz coming out of the sample. And this is because the index contrast of the semiconductor and air is very big. Gallium arsenide has a 3.5 3.5 refractive index and R is 1.5. If you make the math, only 2% of the photons being generated at 1 gigahertz come out. And once they are come out, they come with an angle of 90 degrees and cannot be collected in a lens. So photonic engineering means let's make things better. So let's construct a photonic environment where the near field is propagated to quasi-normal modes into the far field and into my collection optics. And of course, this has been done in the literature, including by us. We worked a lot in photonic crystal cavities 10 years ago, but we needed a device, a specific design for our device, okay? And this is what we have done. We have designed a photonic, nanophotonic antenna, which exploits a completely new concept. It's a hybrid between a Mie resonance and a TAM resonance. And the idea behind this is to be able to extract photons, not from the surface, as everybody is doing, but through the substrate. Why we don't want to use the surface? Because we don't need to access the surface anymore. We don't optically pump the sample. The sample is already pumped. So whatever single photons that are coming out of the sample are coming out by themselves and can be collected on the substrate. And this opens a completely new venue for design, okay? So we designed this structure over here, okay, in such a way that on top we have a metallic mirror, which is also the electrical gate for tuning the wavelength, okay? We did this through an inverse design approach. So we set up what were the wanted features and made an algorithm to minimize all possible parameters, okay? As before, this is good because now we can use something that nobody's using, that is flip chip bonding packaging. So we can construct our device, flip chip bond to a ceramic substrate, so all the electrical paths are down, okay? And on the substrate side, work separately on the collection optics, okay? We don't need to solve all problems at once. It can be solved by different ways. And this is actually what opens the venue for scalability, the fact that we can do flip chip bonding. So we don't need to do wire bonding and then finding the quantum dot, or wire bonding and then putting a fiber. This can be done at wafer level, okay? These micro bumpers over here, okay, is the kind of packaging that has a CCD, for instance, or a scientific CMOS, okay? So it can be done on high throughput and on funnels, okay? We're fabricating them, okay, at the moment, and on arrays which are compatible with the design, with our previous demonstrations and this. So this is the current state. This is the technology roadmap that we have followed to arrive to this point. Okay, so everything started with monoculite, Explora project in 2015 in the middle of the crisis. I was fed up of making many different things, never a focused idea, very different projects, collaborations, and I sit down, well, is there anything new that I can bring? And I bring this idea, okay? So it was the design, the European patent filing. This idea itself opened me the door for 2 European consortiums with a European network of metrology centers, okay? Where we iterated on this. We are now in the middle of the second project where we are doing this nanophotonic integration. And at the same time, we were in the middle of pandemic at home with the patent already accepted in three different offices. And CSIC asked us, the promoters of this idea, to join the COMTE program, which I recommend to anyone that is thinking about this. They will teach you how to start an EBT inside CSIC, which is not simple. It's not simple. For instance, the universities is different because the science law applies. In CSIC, the science law, the liberal ciencia does not apply. So there are a lot of restrictions and things that you need to do. And then is interfere constructively with the platform, the QTEF platform, or Juanjo Ripoll, okay, where we could grab some funds to upgrade our labs to tackle this kind of development. Our labs were ready to do a TRL5 development and demonstrating it once. But if we want to make a service to companies like us and talk about scalability, talk about the fabrication at wafer level, characterization at wafer level, packaging and all, our labs are not prepared. And this is the fundings that we are securing are to do scalable quantum photonics, okay? Which means we are able to characterize electrically and optically big arrays of quantum photonic components. Okay, the company was started in 2022, and in the first call of Neotech, which is a program of the Ministry of Industry, we participated and we get our first funds. So we started on March last year with the recruitments and the developments of the scalability of the whole device. Okay, so this is the team, the founding team, myself, Jose Llorens, who is my buddy in the Institute of Micro and Nanotechnology, for his expert on simulation, photonics, and band structures in general. Jose Maria Ulloa, he is a researcher and professor at UPM in Madrid. Okay, so he's expert in fabrication and growth. And then we had two business angels way at the beginning to start the whole thing. Competitive edge, I already mentioned. We have a technology that is based on reliable microfabrication materials and processes. It's plug and play. It's electrically operated, untuned, alignment-free, vibration-resistant, and fully compact and fully integrable and ultra-compact in photonic circuits. The IP is protected. Our initial target might be QKD, but there are other applications. And anyway, a single photon source like a laser, we don't know what the applications might be. The laser, when it started, it was a very nice invention without an application, right? A single photon source is a quantum component. It might be used in different applications. Some of them might not be known. And we are at the bottom of the supply chain of the quantum products. And that's it. Market studies sets for 2030 around 10,000 units per year on these market segments. We want to address that, and we are working hard for all kind of directions to get there. And that's it. Hope you have enjoyed. I'm happy to solve your questions. Thank you.
Okay, well, thank you very much, Benito, for this very clear and very nice talk, which I think will trigger some questions. So maybe we could pick up first from the audience here, and then from the online attendees. Is there any question or demand? Yeah, please.
Protocols. No, that's a possible thing we could do, but at the moment we are focusing on reducing the cost. Okay, so in one way we are increasing the performance, but we need to arrive to a performance which can be fabricated on big numbers and low cost. That's the role of a company. So we do not include a process which is not a standard process. In the sense that when we want to really fabricate this at wafer level, we can go to a foundry, a standard one, and get it fabricated. Okay. This means, for instance, that we don't introduce in the photonic design anything which is smaller than 300 nanometers, because 300 nanometers is something that can be fabricated with DUV, not with electron beam lithography. So if we don't rely on electron beam lithography, it can be fabricated at wafer level and locally one shot demonstration. Yeah, I mean they should be competitive with all technologies that rely on the same materials and concepts. So we have 4 spin-off competitors, so to say. I don't count Toshiba as a spin-off competitor, okay? And all of them rely on similar concepts. And in that sense, our numbers and theirs on comparable excitation conditions for scalability.
Well, I have several questions on that. Technically, you said you have several degrees of control in your system, which are better than what was before available. I don't know if the polarization is relevant and whether it will be possible to control the polarization?
Typically, for a QKD problem or for any, the polarization is set after. Okay.
Okay.
So quantum dots emit in an HV basis, typically, unless you make a special trick to make these two states degenerate and they emit.
I think I didn't see in your talk at which temperature we are working and whether this is important. Okay.
Okay, of course. Semiconductor quantum dots have all these beautiful numbers at low temp. If you bring them to room temp, then it's better to have a hexaboron nitride or other material, nitrogen vacancies or whatever. But if you compare low temperature and high temperature, low temperature are better. This typically was the drawback of this technology until it was found that the best detecting technology is superconducting, which is superconducting semiconductor, superconducting single photon nanowires. Okay, so they work at typically 4K as well. Okay, and as far as you are relying on superconducting technology for detection, it doesn't matter whether you rely on a low temperature for emission. So this is not a technology as it is explained today to be in a mobile or things like that or portable. Okay, but it is something that can be easily fit in a 19-inch rack. Okay, because in a server room, you have things that consume more than a miniature closed cycles.
I don't know if there are more questions because I have a third one, but at least if there are more questions. So my third and probably last is I saw that you have multiple dots actually in the slave.
Mm-hmm.
The reason is that in this way you get it's easier for you to do the experiments, or is there any limitation?
No. This is a drawback. That's why we put them on an array to be able to control how many and where they are. But when you try to do that, the optical properties of the quantum dot and saturation characteristics are not as good as self-assembled ones. The self-assembled ones, quantum dots are grown because after a straight relaxation of a two-dimensional layer of semiconductor. So you grow a semiconductor which is a strain over another semiconductor, and the way of relaxing the strain is forming the quantum dot. And when this happens, you don't know in which position the quantum dots are going to appear. But today, what does is making deterministic coupling between the photonic cavity and the quantum dot, knowing what the quantum dot is. Okay, and that's the way they are being fabricated now by others. They have other possible routes.
Okay, very nice. Thank you very much. There are apparently no questions through the. So if there are no more questions, it's the last chance. If not, I would like to thank Benito Alem for his very nice and give him all our support and success for the future. Thank you very much.